So now that we have looked at the present value as a concept for comparing future cash and present cash, let's study some mathematical shortcuts that can make calculating a stream of cash flows easier. So we started talking about a checking account, and let's suppose that I put $100 into my checking account. So that's year zero. And that checking account pays a 5% interest rate. So if I put $100 in that checking account, if I let it sit for a year, at the end of year one, I'm going to have $105. Now, if I leave that money in the checking account, we'll have 105 times the discount factor, and you end up with more money, right? We get the interest earning interest, which makes a little bit of difference, that 25 cents. So what we're going to do instead is pull out all the money. So I'm going to pull out $5, which makes the total 100. So I have $100 in it in year zero. I pull out $5 and I have $100 in year one. The same thing happens in year two, and so on. So at a 5% interest rate, we could pull $5 out every period. And let's say we did that until year 5. But then in year 5, we're also going to pull out the balance. So we end up with 0. So it's pretty clear what that would be worth. I put $100 in, and I get $5, $5, $5, $5, and then $105. So that is worth $100 at a 5% discount rate. And so if someone offered you a security that pays 5, 5, 5, 5, 105, we could use the discount factor to figure out the present value of all of that money. So 1.05, so take this $5 and divide by 1.05 squared, and take this $5 and divide by 1.05 cubed, and take this $5 and divide by 1.05 to the fourth, and then this divided by 1.05 to the fifth, and then add all those present values up, and we get, unsurprisingly, $100. So pulling $5 out every year, the exact rate of interest, and then pulling the principal out, gives us a present value of 100. And the fact is, it doesn't matter how long we did this for. If we had 5, 5, 5, 105, it would still be worth 100. If we did 10 more 5s, it would be worth 100. And in fact, if we did, if we could have as many 5s as we wanted, as long as we wanted. So let's say we did 1,000 years worth of 5s. So what's going to happen to that last $105 payment? What's going to be worth 1.05, the discount factor to the 1,000. So it's worth much, 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 much less than a penny. We wouldn't even have to go to 1,000. What if we did 100 years? Then you've got maybe 79 cents. So the reality is, at that point, the fact that you get your principal back doesn't make a big impact on the price. And so if I get 5, 5, 5, 5, 5, 5 for 1,000 years, that's indistinguishable in price terms from 5 forever. 5 forever actually is a real security. We call it a perpetuity, or in some cases a console. The Bank of England issued some of these at one point. And it's just a promise to pay a certain amount of money in a consistent manner in perpetuity, for forever. And we can see by this same logic that 5, 5, 5, 5, 5, 5, 5 forever at a 5% discount rate is worth exactly $100. And this series here of this decreasing present value actually has a nice, concise mathematical formula that summarizes it. So this is the geometric sum formula. That's not really important to know the name. The importance is the application, which is to say that the value of a perpetuity is equal to the coupon, or the amount paid every period, in our example here 5, divided by the interest rate expressed as a decimal, and that's it. And we can see how that works for our $5 case, because we take 5, we divide by 5%, and we get $100, which is what this stream of 5s forever is worth. So valuing a perpetuity in and of itself isn't particularly interesting, because they don't come up that much, but it's a useful formula for deriving other more important pricing formulas.